be familiar with a few of the assessment techniques, and I can tell you to really understand and be able to use these techniques, this would call for a whole semester of lectures. But the idea, going back to the learning objectives, it's important that we understand the different frameworks, okay, for the climate change impact, adaptation, vulnerability, and what are the various methods to generate the climate scenarios. So I try to pull some key points from the module that you have. Okay, and it's good that all of you have that, so you can underline some important points so that those points remain with you. So a key component of climate change adaptation effort, and this is important. Before you can make any sort of climate change adaptation effort, you have to make a reasonably reliable assessment. That sticks with me. Before you can talk about adaptation in the context of your country, you have to be able to assess a reliable assessment of the potential impacts on the different projected conditions. And that's where your scenario building comes in useful. Okay? And scenario building, colleagues, is something that you can sit and do. For St. Lucia, you can say, supposing we have X amount of people in a particular community, and this community is already spatially exposed to hurricanes. If we're going to have more frequent and more intense hurricanes, but more people are allowed to migrate to this community, how would it change? How would the dynamics change? Supposing the government decides to introduce a sort of zoning law, zoning regulation that identifies this area as a high-risk area and stops people from living in the area. How would it change? So what I'm saying basically is that we're looking at different projected conditions. Now the problem that we have, and it goes back to some points that we made yesterday, that this reliable assessment depends on data. And data, plural, are generated by research work. So that if we don't see research collecting the data, analyzing the data, interpreting the data, and understanding the implications of the data, what the data is saying to us, then we can see where adaptation becomes some sort of, it is not given the depth of thought that we think it should. And so when we do our adaptation strategies, maybe we say, okay, let's just think about how we can increase the height of the seawalls. Let's talk about how we can diversify the economy. Maybe we just go into ecotourism, and we don't understand specifically how we prioritize the different adaptation measures based on what the impacts are. And then another important point that I picked up in your modules, that assessing the impact of climate change on water resources is conducted within a larger framework. It goes back to a point we made yesterday, not taking the silo approach, but understanding the importance of integration, understanding the importance of how things are interconnected in the real world. And so if you have already frameworks that have been tested, assessment frameworks that have been tested, why go and reinvent the wheel? Why go and reinvent the wheel? Even before we started talking about climate vulnerability studies were done for disaster and disaster risk reduction. So there are many things that we can learn, and this is important. And so the aim here really is to support selection and formulation of adaptation policies and measures that would enhance resilience. Now obviously resilience is the opposite of vulnerability. So once you want to enhance the resilience of your water resource systems, you're going to ensure that this is always upheld. The IPCC, Intergovernmental Panel on Climate Change, as all of you know, and you should read their reports. Yes, you might say the science and abstract and so on, but if their reports are worth reading. So the IPCC, that's really an authority, because you know that there are hundreds of scientists that belong to that comprise this IPCC. And so this is why when they say something, we pay attention. Because we're not talking about one or two, we're talking about hundreds. Now, they have identified 5 types of the CCIAV, and we will look at each one. And they've been able to differentiate them by purpose and focus on assessment, the available methods and the approaches. But this statement here is more important because the assessments are shifting focus from being mostly research-centered, research for research's sake. We spoke about that yesterday. So we have wonderful pieces of research for research's sake. They're trying to shift that, and that's important because the science is always critical. The science gives us the base upon which we make decisions. But apart from the science, the research must also support policy analysis and decision making, adaptation assessment, vulnerability assessment, integrated assessment, and risk management. What I like about this is that we're talking about assessment, and then here, how do we manage risk? Because the risk-based approach, and in risk management, we have to identify the risk, we have to analyze the risk, and then we manage the risk. It's a process. We do it all the time in EIEs. We identify the risk, we analyze the risk, and then we manage the risk. Now, so for each one, there is an explanation, and you have this in your books. Impact assessment, forest generation, very top down. Important. It's top down and it still dominates. You look at any literature, impact assessment dominates. There are different typologies of impact assessment processes, but impact assessment still holds true. Because in impact assessment, you can do it at the project level, you can do it at the policy level, okay? And you can even look at this in the context of sustainability, because we can even look at sustainability appraisals. So the impact assessment is important. And that is where a lot of modeling, yesterday we talked about the global climate models. This will fall under impact assessment. So for natural scientists, you will love this. Because once you like physical models and you like to play around with math, right? Because a lot of these models, it's mathematical equations and all of that. If you're a hydrologist, so you know that. Okay? A lot of mathematical equations, but there are people who love to do that. And so in impact assessment, you have a lot of that. But it's very top-down, scenario-based. And it's based on a number of assumptions. So sometimes when we look at models, even in our own studies, you start looking at what are the assumptions of this model, and then you say, man, but the assumptions are not relevant to my country. Or you might say, a few of these assumptions, no. And because of the assumptions, you want to find alternatives. So this is how we can move to other types. The adaptation assessment is bottom up. You have top down, the bottom up. And we're talking about assessing, appraising measures that would enhance the resilience of a system that is exposed to the risk of climate change. And we're getting there. Some work has been done on this. This is the one that I love, vulnerability assessment. Because it's bottom up, it is associated with adaptation, but it focuses more on the risks themselves to reduce their impacts. And what I love about the vulnerability assessment is that it allows me to really address the root causes of vulnerability. So that if I'm doing, I have done the vulnerability assessment, social vulnerability assessment for the Cayman Islands 2 years ago. So it allows me to look at all the parameters and the indicators for social vulnerability. And then to map that, to superimpose that with the exposure, the physical exposure. And then to show high-risk areas would be a combination of exposure, where you're located, along with your socioeconomic conditions. And then this is the other one that I really like, is the integrated assessment. And I will show you how this is done, because the integrated assessment is really fun. And we've done it before, and I'm sure that you've done it, but maybe you didn't call it integrated assessment. And because we're talking about ecological system, and we're talking about how things are connected together, then even factors are connected, physical, social, and those sorts of things. And then the risk management, where we characterize and we manage uncertainties. So these are the 5 that IPCC has identified. Trying to identify the characteristics of these 5 approaches, they have used some basic thematic areas: the scientific objectives, and you can follow in your books, please, the practical aims, the research methods, the spatial domains, scenario types, and motivation. And if we just say, maybe just, let's look at for the impact, because we said that one is fourth generation. Scientific objectives, the impacts and the risks on the future climate change. If you go back to the handouts I gave yesterday, we talk about climate projections. Climate projections, and how these climate projections, how they're made. And they're based on modeling, and they're based on certain assumptions on these different conditions. Practical action, practical aims, actions to reduce, we want to reduce the risk. What are the research methods? For impact, we can actually use, I don't know how many of you are familiar with DPSIR. How many persons have used that? Because DPSIR would be, what are the drivers? So poverty, all of those things will be drivers. What are the pressures? What is the state of the environment? What is the impact? And what is the response? A 7-step assessment framework. And I think this is in the book. The first one would be to define the problem. Now all of us are graduates, right? And sometimes this is the biggest problem. What is the problem? Defining the problem. And we start with that. Now once you define the problem, and this is why it's important to be able to differentiate between symptoms and causes. Because when you know the problem, you get to the root causes of the problem, then what's your selection, you select the method of assessment. So with climate change, we know that the problem is the concentration of greenhouse gases. The root cause has got to do with lifestyles of consumption, production, and all these sorts of things. But we're talking about greenhouse gases, as Mahendra told us. And so when we select our method, that's when you will say, am I going to use my global circulation models? What kind of a model am I going to use? And then you test it. You test it because you want to know the level of sensitivity. How will it be able to identify or project the impacts with some level of certainty? You then select your scenarios, and that's where you have to build in different conditions, different socioeconomic conditions. If there was enough time, it's nice for the groups to actually build their own socioeconomic scenarios of some dream country, of what will happen, you know, and how that's going to impact on greenhouse gas emissions. So you select your scenarios, and once you do that, colleagues, you then assess the biophysical, and I already explained what that is, and your socio-economic impacts. But always in your assessment of impacts, don't decide that because you like the physical sciences, you're going to look at biophysical alone. If you're a social scientist, don't think that the impacts will only be that, because in the real world, as a result of a change in the biophysical aspects of the environment, the socioeconomic aspects will be affected. The next step is assess autonomous adjustment. When you see the word autonomous adjustment, what comes to your mind? What is autonomy? Yes, it's automatic, so it seems as if it's not planned out well. What else comes to mind? It also says as if it's done in a sort of silo fashion. Not only automatic, not only immediate, it's not planned and so on, but also it's like a separate kind of, it's a response that doesn't consider all of the other variables or all of the other elements that can impact on that decision. But sometimes in life, in dealing with changes, climate change, this might be acceptable. In any case, sometimes our policymakers, this is what they do at any rate. But I'm speaking as an academic, right? And then evaluate your adaptation strategies. And I like this, you've got to evaluate. You have to evaluate your adaptation strategy. So even as you have adaptation plans for your country, because it's more, you can read the theory. What I want to ensure here is that we understand the practical aspect of this. So you go back and you make a change. You have to evaluate it. So your boss calls you, it is climate change, in our second national communication, these are the measures. But as a technical officer, which ones you think we should put in for this year's budget? And you think you're going to close your eyes and say, whatever we say, this, whatever. No. It has to be something that you evaluate properly. Okay? Maybe what's the risk? It has to be based on some criteria so that you have priorities set. Alright? Remember, we talk about impact, and we said the assessment is the one that is very common, very popular. But colleagues, in the assessment, there are different types. So for climate change scenarios, there are 3 types that one can look at. The first will be the scenarios that are based on outputs from the global climate models. And this one is very, very popular. Scenarios that are based on outputs from the global climate models. And that's why yesterday I gave you a little handout on that. Not a lot of reading, but you know, it's good to read. And then synthetic scenarios. Synthetic, what comes to mind? Because once you hear a word, something automatically should come to your mind. Pardon? Yes, very artificial. And I'm sure already you're thinking that you have a problem with that one, right? Because synthetic scenarios. So it's a sort of make-believe that these are the assumptions, this will happen. And then you have analog scenarios. Now, for those of us who do impact assessment, you know, we can use some analog models where we say that this happened in the past. So let's use the same scenario and say what can happen. The general circulation models. They're computer applications that are designed to simulate the Earth's climate system. So this is where you put in all the climatic factors here, the climatic variables. So for climate, we're talking about precipitation. What else we talking about? Evaporation. What else? Temperature, runoff, and all of that. And that's why sometimes even in my classroom, I ask students what's climate change. As soon as they say global warming, I say wrong. It is not synonymous. Global warming is a subset of climate change. Climate is more than temperature. So what they do here is to have all of the climatic variables, the parameters in the models, but what they have it all the different socioeconomic circumstances based on assumptions. So if you have more greenhouse gases, what will happen to the climate? You simulate. And simulation is quite good because it's like a world you're trying to create. What will happen if, and you're simulating, but it's computer application. So obviously, even in simulating climate, you have to write some equations. How many of you like to write equations? Oh, I don't see any answer. All right. And then you have, for this, you have a range in complexity. So it can start from the simple energy balance models to the 3D general circulation models. So simple ones that you can copy at home just on your computer with the simple energy balance. But then the 3D, that is high tech. And then you have, of course, the state-of-the-art in climate modeling that is represented by atmosphere and ocean. It's known as AOGCN, because you have that interaction between atmosphere and ocean. So different parts, the hydrosphere and all of that will be modeled. But at the end of the day, you're getting closer to reality. The equilibrium run, where you have both current and future climates are assumed to be in state of equilibrium. There's a big assumption there. Both current and future climates are assumed to be in state of equilibrium. And then you have simulations that are executed assuming doubling or quadrupling of greenhouse gas concentrations. But for equilibrium, it's low computation cost, but it's all realistic. Well, from the time you see equilibrium, it got to be unrealistic. It's costly to run, and it needs a warming period to avoid underestimating the earliest stage after present. But again, this is closer. This is closer. Because the way we are going, don't you think that there's an increase in CO2? Or you think that there's a possibility it's a decrease? Anybody says opposite? Right, look at the IPCC reports. Now, what are the advantages and disadvantages? And I think you're perhaps, I don't want to go through all of these, but it produces global consistent estimates of larger number of key climate variables, and we talked about this just now. But the disadvantage, simulations of current regional climate often inaccurate. And this is because of the scale. And this is why in the region, in the Caribbean region, I think more and more pressure is put on the MONA group of scientists there to try and downscale models. In a region where data collection is poor, modeling got to be poor as well. Because I can't see, even to write equations, because each of those equations represents something, right? A particular parameter. Because when you have a concept, and we're talking research now, you have to make the concept, turn the concept into variables, and your variables your parameters, and from your parameters indicators. Am I right or wrong? And it's based on that you can really do assessments. So that if we don't embrace the concept of research, the importance, then I can see we will always have a problem with the modeling. And that is why, in terms of our response, we are behind. Look at the man in the mirror. Why are we behind? It is not only because we are vulnerable small island states. There are other things, right? But I will leave Dr. Cashman and others to talk about that. So the synthetic scenarios, they're based on incremental changes in variables such as temperature and so on. They're based on synthetic records, and changes are assumed to be uniform. Very few studies under the synthetic scenarios would introduce temporal and spatial variability. And we know that in the real world, there will be temporal and spatial variability. Go back to the slides yesterday with the world maps, and you would see the different densities of colors that would show the climate impacts. But there are, so advantages and disadvantages. Obviously inexpensive. You can have a wide spectrum of potential climate changes and so on. But this assumption of uniform change, not physically possible. You and I could have said that before. Okay? And then the analog. Remember we talked about GCM, synthetic, and analog. So the analog, they're based on using past warm climates as scenarios of future climate. Now, this very first one catches our attention because past for future. And look at this. It's in your books. IPCC has made recommendation against using analog because the past global warming were not caused by anthropogenic, human-centered, human-induced anthropogenic emissions of greenhouse gases. And maybe that is why at the very start with the climate skeptics they're saying, but we've always had climate change. Go back to geological age. If you look at the geological scale, you will see that the Earth is millions and millions and millions of years old. And so there were periods of warming and so on. However, we know that the acceleration of the warming really caught our attention during the Industrial Revolution. Okay? So they don't encourage us to use the analog. So don't go saying that you want to use that at all. Well, I think that we've already established why we would want to use that. So let me quickly try to wrap up. So the water resource and the climate change. I think I've belabored this point already, that we want to ensure that we consider biophysical and socioeconomic aspects when we look at water resource and climate change. Too much water is a problem, but too little water is still a problem. And the case studies that we presented emphasize that point. Okay? Now, because the impacts of climate change on water resources are complex, it will be unwise for you and I to say that, for you and me to say, sorry, that there is need only for structural approaches. Both structural and non-structural approaches are important. Structural, let's put in some dams. Let's put some reservoirs. Structural approach. Engineers love it. Non-structural, yes, you put your dams and whatever revetment. But at the same time, look at vulnerability. Maybe people are vulnerable because in the first place you got them living in the wrong area. So land use change, non-structural. Are you following? The two must work hand in hand. One time I was asked to do a keynote address on balancing structural and non-structural approach to flood mitigation in the Caribbean. And I said, it's not a matter of balancing, because it depends on the context. Balance, when you think of a scale, Joyce, the balance is not equal. But in a particular context, maybe you need more of the structural, right? In another context, you need more of the non-structural. So it's the context that will determine whether or not we use 80% of one and 20% of the other. But we have to understand the context. And what I'm saying to us today is that in trying to respond, in trying to adapt to the impending impacts of climate change on water resources, we have to consider structural as well as non-structural. UNFCCC in 2005 compiled a number of water resource management models. You have the WIP that will look at water supply demand management policy analysis model, and in fact a lot of persons now are getting it, well, trying to use the WIP. I'm not familiar with this, I've never used it, but I've done work with Professor Padei using SWOT. We've done watershed modeling for Guyana in the Demerara subwater basin. Time doesn't permit me to show you some of the results, but we've used the soil water assessment tool to model the 17 or more subwater basins within the Demerara watershed. Right? So this SWOT allowed us to talk about not only issues of quantity, but also issues of quality, levels of phosphorus and so on in the water. So, and linking that back to agricultural activities and the whole issue of housing and solid waste management and lumber yards and you know, industrial activities. So this was quite an interesting study, and it's used a lot in agriculture. And then you have a suite of models that simulate different components of watershed systems. Watershed management is important. One of the things that I could never understand is how persons who work at entities related to water don't see the link, or a few of them see that link between the water that they have access to distribute and the watershed. So a lot of times when they talk about water conservation, it's about turning off the taps and whatever. But the source of the water, the watershed. And so we still keep this, you know, deteriorating, destroying and disrupting watershed areas because the connection. And a lot of people who live in the city don't know what's a watershed. I didn't call any names, you know.